Good morning. This is Grand Rapids Community College's calculus class, and we have been just introducing some differential equations. And so we talked about just general differential equations, and then we had a set of ones that are called separable differential equations, and we had to try to solve those. Sometimes they had initial conditions, and sometimes they didn't. Um, so I wondered if anybody had any questions from homework. Questions from homework. Start with 9.1, anything of the modeling of differential equations, just in general. Still can't quite hear you. 11? Okay. Okay, so for these situations, we're supposed to look at these graphs and explain why they can't be solutions to this differential equation, which says dy dt equals e to the t times y minus 1 squared. Now, one thing would be if we're in this first quadrant, both t and y are positive, and so this differential equation, e to the t, would be positive. Actually, with this differential equation, the slope's always positive, because e to the t is always positive, and y minus 1 squared is at least non-negative. So there can't be any place, this left one, there can't be any place where the graph goes down, because the slope has to at least be 0. Let me go in a little bit further. So for the left one, because there's this region here where the slope is negative, we know that one can't be possibly the one. Now in the second one, we can even look at this from the other perspective. As t gets larger, e to the t is going to get larger. As y gets bigger, once it gets past 1, y minus 1 squared is going to get bigger. So this slope should not only be non-negative, but it needs to be concave. This slope needs to be increasing, so the original graph needs to be concave up. So you can see here, once we get past 1, 1, past y equal 1, this turns to concave down. So that would mean the second derivative would have to be negative, which means the first derivative would have to be decreasing. And you can tell from, like I said, you can tell from these values that as t gets larger, this is going to get larger. As y gets larger, once it gets past 1, this factor is going to get larger. So the product has to get larger as we move to the right and up. But instead, we have this concave down. So, oh, your screen's on. Just a second here. Hopefully that'll do it. Now okay. So is that okay? I still can't tell what it is. Okay. Was there another question from homework anyone had?
31 and
3. Any other ones for 9.1 before we move on? What about say 13 here? Just because this is a good model there.
9.
So in this case, it was a theory, learning theory. Okay, and they're looking at learning curves here, and they're thinking that P is the performance of someone learning a skill as a function of training time, and the derivative represents the rate at which performance improves. So when do you think P increases most rapidly? Probably initially. You know, when they're totally unskilled and they're just trying to learn, it's probably right initially it should be the steepest. What happens to the PDT as T increases? It kind of levels off. You get to be where you're as good as you're pretty much going to be, and you're supposed to explain. If M is the maximum level of performance at which the learner is capable, explain why the differential equation is reasonable. Well, the two things we said were, one, dPdt should be largest when initially, so when P is as small as it gets, that should be at the largest. So if M's my max and P is as small as it is possible, then this factor is going to be as big as possible. So that means the rate at which I'm learning is going to be as big as it gets. And then the second one was, let's see, what happens as T increases, it should level off. As P approaches, since this is positive now, as P approaches M, this factor approaches 0 and kind of levels off. So it shows a exponential function really that is approaching some maximum value M. And that's one way to look at, depending on what they're learning, this was a skill, so this would be like a manufacturing, you know, maybe they're putting them on a certain job and they want to see how long it takes them to learn it until they're up to what they're capable of doing. And you can decide whether you want them running that job or not, running that machine or not. So anyway, just wanted to go over one more example from modeling. If we go on to 9.3, separable equations. So these are solving differential equations now. And 9.3, you said number 30. Did I assign number 30? 31. Oh, 31, okay, there we go. That makes sense. All right. Turned off, was it on or not?
Still off.
Yeah. I swear that's just what I did. I wonder if there's a problem because I think it turned off. Interesting. I'm gonna have to fuss with the input. I'm gonna have to get somebody to come in here. Anyway, number 31. At worst you can turn your chairs around and look over there if that doesn't ever come on. And I'll try and write bigger. Okay, so for this one we're supposed to find orthogonal trajectories. So orthogonal trajectories means that the slopes of the ones I'm going to find, the family of curves I'm going to find, need to be perpendicular to the slopes of these, the slope of the tangent lines for these. So dy dx for these lines is negative k over x squared. So depending on what letter you want to use, I used Z last time. Is there a favor of yours? The book probably sticks with Y, but I don't like to use Y for more than one thing at a time. Or you can use Y too. Do you like a subscript better, or do you like a different letter? Or? Doesn't matter. Okay. We could always use, maybe I'll do it this way. So Y perpendicular, I'll write it like that with a little subscript. So dy perpendicular dx should be the opposite sign and the reciprocal of dy dx. So negative 1 over k over x squared, which is x squared over k. Now, I'm not going to change out this k like I sometimes do, because this k has to match whatever that k was. So sometimes I would have rewritten that as a different constant just so you don't divide by, instead you're multiplying by it. Okay, so now we want to solve this. So again, these middle terms I'll rewrite it here down in a second. So I have dy perpendicular dx equals x squared over k. I'll just put the differential dx on that side. So dy equals x squared over k dx. And then we're going to integrate both sides. So y equals x cubed over 3k plus some integration constant. So an example, so we can pick one. We're supposed to draw a couple of these on the, so here's this is supposed to be perpendicular. I forgot to write that down again. So let k equal 1, say for instance, just because it's an easy one. Then our original function would be y equal 1 over x. And some examples of perpendicular functions would be x cubed over 3, or x cubed over 3 plus 1, or x cubed over 3 minus 1. We'll just do those three. And we're supposed to try and draw those to show that they're orthogonal, which is another way of showing they're perpendicular. Saying they're perpendicular at all points. Every time they cross, they should be perpendicular. So I'm going to go to y equals and put them in there. But for a minute, just a minute, I'll show you my calculator. I can change my mode here. Alright, so 1 over x is the one I chose. There's my original graph. And then x third divided by 3. X third divided by 3 plus, oops, plus 1. And x to the third divided by 3. Okay. By now you hopefully have copied those down. So this is my y equals 1 over x, and then I have x cubed over 3, x cubed over 3 plus 1, x cubed over 3 minus 1. And now I'm going to zoom standard to begin with. I may have to adjust that. Oops, that wasn't what I wanted to do. I don't know what I actually did there. Okay, let's try it again. Zoom 6. There we go. There's my original ones. There's 3 of these going to come up. But I haven't zoomed in enough to see it very well, and I haven't squared it off, so I'm going to do that in that order. First I'm going to zoom in, and hopefully the intersection points will still show up on this. Okay. But then we have the problem that our screen is rectangular, so it kind of squishes it and stretches it to the right. So then you have to zoom square, which is the 5th one. Which should show it better. And then if you want, you can pick, we can zoom in again, and just pick one of these. So I'll pick the middle one over here, on the right, just to get an eyeball of whether it actually looks perpendicular. There's our first one, and you can see right at the point of intersection, these tangent lines here would be perpendicular. Is that okay, Eric? Okay. All right. So, how about another one? Any other questions from separating variables? Hearing none, I think we're going to have a little quiz today. So let me write it up here. So solve each of these differential equations. We have dPdt equals k times p, and dPdt equals k times p times the quantity 1 minus p over m. And in both cases, I want the initial condition p of 0 equals p sub 0, so some initial population. And for bonus points, if p is population at time t, interpret the constants. That is, in the first one there's k, and in the second one there's k and m.
Say what they represent.
In terms of population and time, say what they represent.
You don't want like a value.
There's not really going to be a value for them. If you want, as part of your interpretation, if you want to say, suppose k was this, then this would mean something. If that helps you describe it, you understand what I'm saying? If that helps you describe it, you can put it in. No books though this time. And I will try to see if I can fuss with this thing. 5 more minutes. So if you could turn those in now, that'd be great. Okay, has everybody had a chance to turn those in out there? Not quite yet. So the first thing to do with these ones are to separate your variables. So if I have a dp as a differential here and a numerator, then I have to divide my p, at least my p. You can bring the k too if you wanted to, but it's easier probably this way. You have to bring the p down to the side that has the dp on it. So I get dp over p equals k times, and then I bring this differential, the one that's in the denominator, up to the right side, equals k times dt. That's separating your variables. This side should only have p's and constants, and that side should only have t's and constants. And then you integrate both sides. So you get the natural log of p equals kt plus some constant. I'll go with C1 for now. To get p by itself, I'm going to take the e to the power, the inverse of the natural log. So p equals e to the kt plus c1, which is e to the c1 times e to the kt. Now, given the initial conditions, I know that p of 0, I'm going to want you to write p naught or p sub 0 for that. That would equal e to the c1 times e to the 0. But e to the 0 is 1, so that means p naught equals e to the c1. So that means p up here is going to be p naught e to the kt. So I'll write that again. P of t equals p naught e to the kt. Standard exponential function for growth. P naught is my initial population. And K is your growth rate. If you want to be more specific about what I mean by growth rate, look back at the differential equation. It's saying that the rate of changing your population per time unit is proportions, equal to K times the population now. So it's a relative growth rate, I should say. Because it's relative to, it's in a percent form rather than in an absolute value form. So that was a couple bonus points there, if you could write that down. We okay with this one? All right. Same idea, separating the variables here. I'm going to divide everything that has a p. Well, actually, you know what? Just because I don't like denominators so well, I'm going to take the 1 over m out front here. So this becomes k over m times p times m minus p. I factored the m that's in the denominator out of this second factor here so that it'll make it easier when I try to do the separation of variables. So I'm going to divide those two factors, the p and the m minus p, over to the left side, and I'll leave the k over m on the right side. And then we're going to integrate. Now, if I'm going to do this by hand, I'm going to use separation, partial fractions on the left side. So this becomes integral of 1 over m over p plus the integral of 1 over m over m minus p dp. pull all these constants out here. So this is a 1 over m times the integral of 1 over p plus 1 over m minus p. And this is k over m times the integral of dt. So I get 1 over m times the natural log of p minus the natural log of m minus p equals k over m times t plus some constant. This minus sign came because in order to integrate 1 over m minus p, you have to use a u substitution, and the u is going to be m minus p, and you end up with a negative sign there. So if I multiply everything by m, these m's are going to cancel, these m's are going to cancel. I can then put these two using log rules. This becomes natural log of p over m minus p equals kt, and I'll just call this c1 times m, I'll call that c2. And now we can solve that for p. It's going to take a little bit of algebra here. So I get p over m minus p equals e to the kt plus c2, which again we can separate that out. E to the c2 times e to the kt. And if you wanted to, right now might be a good time to solve for that initial, well, I'll multiply through. So I'm going to multiply m minus p to that side. You know what? I'm going to write this for now. I'm going to call it c3. Just so I don't have to keep writing e to the power down. Going to multiply by m minus p. So p equals m minus p times c3 e to the kt. So m c3 minus p c3 e to the kt. And I'm going to add this pc3 to this side. So p plus pc3 e to kt equals mc3. Factor out the p. I forgot to write the e to kt here. And then we'll divide. And I lost you. Sorry. Now, with the two C3 e to the KTs there, they may choose to, it may be easier to multiply through by 1 over C3 e to the minus KT on the top and bottom, just to make the form look better, I guess. have left? We have to figure out the initial conditions and figure out what that 1 over C3 thing is going to be. I could write it as C4, but let's, yeah, I guess I will. I'll call it C4, this part right here. So P of 0 equals P naught equals what I get when I plug in 0 for T. So C4 plus 1 equals M over P naught. Or I sort of switch their places. And so C4 is M over P naught minus 1. Which is sometimes written as M minus P naught over P naught. There's a lot of algebra to get to finally where we say P equals M over M minus P naught over P naught e to the minus KT plus 1. So P naught is our initial population. K is actually going to be just the initial growth rate because it's going to change. And then M is the maximum population, sometimes called carrying capacity. As t goes to infinity, you can see the e to minus kt goes to 0, and I just get m over 1. And if you look back at are we okay with this? Can I take this away or not? And if you look back at this initial one, the two equilibrium points are the ones that make these factors 0. So if the original population is 0, of course there's no growth, because without people you can't have children. And then here, if p equals m, this factor goes to 0. So if the population ever were to reach that maximum, it would stop growing. Those two. Those two are this next section from homework. One of the reasons I put this on the quiz is that these are the basis of the next homework set. Okay. Okay, were there any questions? That's right. We doing okay? Questions at all about those quizzes? Okay. Did you guys get your tests back out there? Okay. Did anybody have any questions from the test? Did they say 3? Is that what you said? 1B? After I printed this, I realized that this was printed like our screen was. It's not like our calculator screen. This isn't squared off. But essentially in 1B, we're supposed to rotate this around the y-axis. And if we rotate this around the y-axis, you end up with two surfaces that compose the two surfaces in a sense. It's really just one because we're taking this and rotating, but there's an outside surface where you take this edge and spin it around the y-axis. And there's an inside surface where you take the right edge and spin it around the y-axis. So you end up with this, I don't know, upside down bowl sort of shape, except that this looks like it comes in more. So anyway, so in order to get the surface around the y-axis, you need to think about how far, again, I'll just pick the one on the, here, well, I guess I need to. I'll just pick the one on the left here. How far is that? Because we're going to take 2 pi r times that. So this distance is actually the absolute value of x. Or if you want, you can use negative x, since x is negative throughout this whole region. That's how far away, no matter which of those surfaces you're using. And then we have our standard ds over here, which is going to be the square root of 1 plus dy dx squared. It's the differential length, arc length. So generally the arc length is given by the integral from a to b of 2 pi times that distance, radius, times my ds. So in our case, it's going to be the integral from -1 to 0 of 2 pi times negative x times the square root of, well, there's 2 of these again. So one of them, when y equals x cubed, I get dy dx equals 3x squared. And if y equals x to 1/3, for that one, dy dx is 1/3 x to the minus 2/3. So if I take this first one, dy dx squared would be 9x to the 4th. And then we're going to do the same integral. 1 plus this one squared is going to be 1/9 x to the minus 4/3. I gotta not forget my dx. I had quite a few people try to put that somehow together into one, under one radical from one integral, but they're 2 separate surfaces, so you need to have 2 separate integrals. And it comes out to something like 9.5, or depends on how accurate you want. Is that okay? Were there any other questions from the homework and for the test? D, did you say? Okay. Let's figure out where. 1D. So in 1D, we're supposed to assume that there's water right at the x-axis, and we're trying to figure out the hydrostatic force on this. So you're going to take slices parallel to the surface of the water and describe how far the depth is, and then how wide is it. Depth and width. So you need a variable. If you want to stick with y, you can. Again, though, y is going to be negative as you're going down here. So if I guess a lot of people did. So if you stick with y, since it's already the natural, this depth is going to be given by negative y. And the width is going to be the left equation minus the right equation. Now, the left equation was the x cubed. And the right equation was the x to the 1/3. But you'll notice that the slices we make have a dy as the thickness. So if our differential is dy, then I need to solve these for x in terms of y. So this becomes x equals y to the 1/3, just the opposite. And this becomes x equals y cubed. And so it becomes y cubed minus y to the 1/3. Okay. So since the measurements were given in meters, you're going to have the 1,000 times the 9.8 or the 9.81 that you need times integral from -1 to 0 of negative y times y cubed. Excuse me. Yeah, y cubed minus y to the 1/3. And when you do the integral, I should write this out here, huh? When you multiply these two, you get y to the 4th and y to the 4/3. So when you integrate, you get y to the 5th over 5 and y to the 7/3 over 7/3. And you're going to plug in 0 minus what you get when you plug in 1. Something like that. I might have my signs off here. I think these are reversed, I think. So it ends up being 2240. I think my signs are those ones are reversed. But the key was two things were, one is get the y value here as depth, and then solve these for y. What'd you say? I'm just going to pick negative 0.3 here as an example. So if the y value is negative 0.3, and I'm looking at the depth of the water, and again, the water is here at the x-axis. So this length here represents my depth. Is that distance 0.3 or is that distance 0.7? The depth. Does that make sense? So whenever, again, a great idea in problem solving that I would, some of the things I would like you to take out of this class don't have anything to do with calculus. One of them is problem solving. If you're having any difficulty figuring out whether it should be one thing or another, rather than just stick to the formula, draw a picture and plug in a number, like I just did here, and ask yourself what makes more sense. Try to connect your common sense, because you guys all have pretty good common sense, to solving the problem, rather than just follow some formula. I would recommend that. Anyway. Any other ones? Okay. All right, so let me go through a couple more the problems from tonight's homework. So I'm going to do number 4. I didn't assign number 4, but one of the questions we assigned is kind of like number 4. So in 9.4, one of the questions is going to give you some data, and tonight at least one, maybe two. And we're going to look at this data and try to decide whether it should be that first model we had, which was an exponential one, or that second model we had from the quiz. The second one, by the way, is called the Logistic Model. So first thing I want us to do is to plot these points. See, the Logistic Model. So an exponential model is going to look like this, where there's some initial population, but then it just keeps growing fast at a faster tangent, so that it's concave up. But the slope's always proportional to the population as it was. The logistic model has some maximum value. That thing we mentioned, it was called the carrying capacity. And what it has is, it's concave up for a while, and at first it's very similar. If you were to zoom in on this left side, it should be very similar to the exponential model. But the further over you go, pretty soon, about right here, when the population's halfway between the initial population and the carrying capacity, it changes from being concave up to concave down and approaches that max. So the question is, which kind of a population model do we have for the data given? So, let me see if we can use our calculator. Before I use my calculator on this, I almost forgot. I wanted to show you guys how to use your calculator to solve differential equations. Now that you had to do them by hand for a little. If you go to the calc menu, the very last one listed is dissolve, and it's not an Italian name. It's DE solve, as in differential equation solve. So when we take that one, you have to type the differential equation. So for instance, that first one would have been P. Now instead of dP dt, what you write is P prime, but the prime is in blue above B here. So anything in blue, you have to hit the second key first, and prime equals K. Now again, don't forget to put K times B, because if you put KP together, it'll think of it as one variable, comma, and then you have to fill out the independent variable, which in our case was T, and then the dependent variable, which in our case was P, and then close it and then enter, and it solves it. Now when you see this little at symbol, it's just saying there's a constant there, integration constant there. Now what's kind of cool is I can put some initial conditions on this too. So if you put a space bar, and then you tell it the initial condition, P of 0. Unfortunately, I can't put P sub 0 here, so I'm going to use a different letter. I'll use Q. And Instead of P naught, I'm going to use Q. And it'll stick Q there. Q e to the kt. Now I can go do the same thing here for my second one. 1 minus P divided by M. And it solves that. Now my calculator left it in the form where I have Q e to the kt in two spots. P naught e to the kt in two spots. Whereas I think when I did it by hand, I solved it for e to minus kt. So I have this is 1 and this is like m minus q over q times e to minus kt. But anyway, your calculator does do some differential equation solving, which is kind of nice. If I want to graph, though, some plots, I'm going to go to my applications, to my data matrix, and I'm going to open one. Oh, and I got to give it a variable is x. Okay. I should have used t, but I want to plot, I guess I say. So I'm going to put in the data that was in there in number 4. It was every 2 hours up to 18 hours. And they had yeast cells. Anybody ever done that in biology? Yeast growing on the petri dish? Okay, and we want to try and plot set up here. So plot 1. Oops. Instead of me, I got something in here last time, so I'm going to use C1 as the X variable and C2 as the Y. No frequencies. So if I enter that, okay. And then I got to go back to my graph. Oops, and I want to set that up. I keep doing that. I'm going to turn off my Y equals. There's our consumer surplus from earlier. Or no, this is the orthogonal trajectories, wasn't it? So I got to clear these out. And I want to change my window. So 0 to 20, say, by 2s, and 0 to, say, 700 by 100s, and it should draw me some. There we go. So we'll plot the data and use it to estimate what? Does this look more exponential or more like the logistic curve? And it's clearer, it looks more like the logistic curve. It's concave up, but then right in here it starts to go concave down. They're going to want you to do both models. And if I were to estimate the carrying capacity, 700 looks like it's about right where I put the maximum on there. Maybe just barely less than that. So I'm going to go back to my data and do some analysis of this. So under Calc F5, I want to do exponential regression. And I'll put that in Y1 here, C1, C2. Oops, and store that into Y1 of X. And so it gave me a initial population of 35.6 and it writes this differently. It doesn't write it as e to the kt, it writes it as just b. But if e to the kt is about 1.225, then k is around 20%. Okay, so that should be stored in there. And then I want to do it again, only this time instead of exponential regression, I'm going to do a logistic equation, which is down under C here. And everything else is the same, except I want to store it in a different y. It takes it a little longer to figure out the logistic equation. But hopefully it'll get there. Well, I'm waiting for this. I should tell a joke, huh? Like Dave used to. So, here was a joke I saw the other day. We interviewed anyway. That's a good joke. If you know binary, it's funny. If you don't know binary, it's not so funny. So my calculator's finally figured this out. Now you notice again, this is still a logistic equation, but it writes it in a totally another different form than the one we had. So there's like 3 or 4 different forms that none of which are totally standard. So it's harder to picture what's going on here. But if you think of since c is negative, if you think of x approaching infinity, this e to the cx, that's going to go to 0. So I get a over 1 plus d. So a plus d is my carrying capacity. So 658 there, plus 13. That should be about the carrying capacity. So it's got about 671 as the carrying capacity, as its estimate, which is less than even the last number here. So that'll be interesting to look at. So now I'm going to go back to my graph. So here's my exponential, and you can see how it's fine for a little while, but pretty soon it's too low and then it gets too high. And then there's the logistic equation, which was much better. Not perfect, but much, much better. And then if we were going to use, so if I was going to predict something, I would use the logistic model and predict some data value. Okay, so that was one type of question from tonight's homework. There's one other one I want to talk about. So this is supposed to be another model for fish population. Now, why would they use this one? dPdt equals 0.08p times 1 minus p over 1,000. If I didn't have the 15 on here, this would look just like our logistic equation. Right? Except, and so what would the 0.08 represent? What did we say the k was? the initial in an exponential equation, it was the constant rate of change, 8% per year per whatever t unit. In the logistic equation, it becomes the initial growth rate. So initially, the fish population is growing at 8%. And what was the 1,000? Yeah, it's the max, or the carrying capacity. So our whatever lake we're talking about with the fish here had a carrying capacity of 1,000 fish. Okay. So why would I maybe want to add minus 15 as part of my model? So these other ones are, in theory, what's happening in nature. The growth is because fish have baby fish, and if you combine death and growth, this is the rate of change. 1,000 was because that's all the reason we have this logistic equation is because the lake only has so much food in it, and as the fish population reaches what the food can sustain, that's where it's going to max out. 15. If every year I catch 15 of these fish, then this is what's happening. Okay. So some constant rate that doesn't depend on the population, because the fishermen that come to the lake don't come. The assumption with this model is that they come and just fish. It doesn't matter how many fish there are. They come and fish, and they try to fish till they catch one, or in this case, they fish till they catch 15, and then they leave. Or they fish once every week and get one a week for 15 weeks, whatever it is. But some constant over here could represent a constant removal of fish from the lake for whatever reason. Is that okay? So again, I might want to factor out the 1/1000th here. What is that going to be? So this is 8 over 100 divided by 1,000. It's 8 over 100,000. And if I want to be able to, what do I want to be able to do with that? And I don't even know if I can do it that way. I'm going to have to go back at that again. Hang on a second. We're going to try this a different way. So I'm going to multiply this out instead. Okay. So if I wanted to, I could factor this minus 0.0. I guess I would like, personally, I would like to do that. And 15 divided by whatever that is. Let's see if that comes out to be something decent too. 15. 1, 2, 3, 4. Oh, great. I just like working with whole numbers better than I do decimals that are small or fractions. So separation of variables, I'm going to pull this thing down to the left. So I have dp over that. So that thing factors. And then we're going to try to integrate both sides here. Which means I have to do my partial fraction stuff again on the left. So 1 over minus 750 plus p minus 250 plus a over p minus 750 plus b over p minus 250. I guess I could have stuck in Okay, so now we can take those back up and do our integrals here. The natural log of p minus 750 minus the natural log of p minus 250 equals negative 0.00008 t plus some constant. And then I'm going to multiply both sides by 500 and put these together. C1, I'm going to call C2. Take e to the power. Call this C3. And now I only have like 2 minutes left here, so I'm going to use my calculator to solve that thing to do the algebra, because it's going to take me too long. course, I might not be as pleased with the result of the formula, but it tells me P is 250 times 3 times e to the negative 0.04t minus my k, or minus my, my C3. Divided by e to the minus 0.04t minus C3. So according to this model, as t goes to infinity, these two terms are going to go to zeros. So I'll get 250 times negative C3, whatever it is, divided by negative C3, which comes out to 250. So according to this model, population is going to have an equilibrium about 250. So because, even though originally the logistic equation would have predicted it to be at whatever that m was, in the original one, 1,000. Because I'm fishing, it levels off at 250 instead. Okay. All right. Try the homework. And then next time you may want to make sure you bring your calculator if you haven't been, because we're going to do some parametric and polar equation stuff. So.